Okay, thank you very much for the introduction. So it's my great pleasure to be invited to give a talk with this title, and it's the first time I talk about Skyrmion in my career life. So if I have made some mistake, I hope you can correct. So my presentation will include 4 parts, and first I will give you a short, brief introduction and the background, and then I will introduce Skyrmion-based synapse and neuron. So the motivation of neuromorphic for the computing is very clear, that the conventional architecture based on phenomenon suffer from the energy bottleneck. So that's why many people are working on neuromorphic or artificial intelligence stuff. So based on CMOS technology, IBM have a new chip based on really spiking neural network, but the energy of this chip is still very high. So even the perspective neuromorphic is very energy efficient, but with CMOS it's very difficult. So that's why actually the majority of the neuromorphic community focus on the resistive memory area, thanks to the advantage like multi-state. So in the case of all this memory, they can perform the many states similar to biological synapse, and they are non-volatile. So recently there is a very powerful chip that can be perform unsupervised learning has proposed. I think this is this committee of RM already achieved a very high level integrated circuit for neuromorphic computing. So it's, in my opinion, far advanced than the Spintronics community. But there is still a very interesting work in Spintronics for neuromorphic. So one example is has been introduced this morning by this work before by the group of Julie Goli. So by using the integration oscillator, so you can see that the recognition of voice can be much higher, improved. But some years before, there are already some work similar to resistive memory. So this work was proposed by Damien Qualios some years ago. So we worked together for this simulation. So the idea is to using the stochastic effect of magneton junction. In this case, we can perform the learning with the array, cross-bar array of magneton junction. But compared to RM, so there are still some disadvantage, like the low magneton resistance limits the electrical output. So in order to make a multi-level storage, so we also propose a PMT compound to get multi-level. So this is theoretically work, but technological is very challenge to get many magneton junction to deposit together. So the opportunity of Skyrmion, I think it's opened a new route for Spintronics to touch neuromorphics. Some years ago, I wrote an overview paper about how to integrate Skyrmion for electronics. So in this paper, we talk about it's possible to make a memory magneton junction, and in particular for neuromorphic. Axel did a very good overview this morning, so I can skip many slides for the introduction, but the basic fundamental of this type of Skyrmion based on interfacial DMI. So this could be modulated from 0 to very large, thanks to the multi-layer configuration. So based on this modulation of interfacial DMI, the small Skyrmion can be generated. So why Skyrmion is useful for neuromorphic? I think the major advantage of Skyrmion is it's particle-like. So in the case of motion by sending a spin Hall current, the Skyrmion can be moved in the nanotrack, and it can pass through the defect. So this behavior can be used with a number of applications. For instance, we explore this behavior for restrict memory, but I think the key performance of this device should be use the voltage control, because the initial idea of restrict is just the motion of Skyrmion. There's no storage. So when I saw the first proposal, so a Skyrmion moves in the nanotrack, but there's no storage. So it's a very strange concept. So by using voltage control, it's possible. So it's not like the restrict proposed by Stewart, because in the domain wall motion, when the current is stopped, the domain wall is stopped by the pinning in the edge, but the Skyrmion cannot stop. So there is no storage in the initial proposal. So we use voltage control to pin the Skyrmion. This could be very useful, and I will come back to this behavior for the neuromorphic part. There is also some proposal like Daniel to propose probabilistic computing. So based on this particle-like behavior, a number of new computing can be explored, because Skyrmion, the advantage of Skyrmion is just the only particle-like information carrier up to now. So that's why it's very interesting. So if we regard the biological synapse, so there the transmission of the information is very similar to the working mode of Skyrmion. So this is a structure of chemical synapse. So there is something voltage gated calcium channel. So that's why I propose to integrate voltage control on this channel. So it's very important, because there is some similar behavior in the chemical synapse. So there's a neurotransmitter to transmit the information between the pre-synapse and the post-synapse. So this is very similar like this. If there is the one of the part of synapse and another synapse, this part could be considered a synaptic cleft. So if we regard the chemical synapse, the most closely bio-inspired behavior should be Skyrmion. So it's not RAM or other memory can have this similar behavior. So this is why it motivates. I have two PhD students. They are very excited to work on this topic. So in this type of biological neural network, there are major two-part synapse and neuron. So that's why I will talk about independently. The first example is synapse. So I will give you two examples of synapse. As I mentioned in this behavior, there is voltage control this channel, and there is a synapse cleft. So in this case, we design a device like that. There is two parts. So one is the pre-synapse and the post-synapse. There is a behavior barrier here. So this barrier can be controlled by a voltage to define if the skyrmion can pass or not. And when we send a spiking pulse from this side, the skyrmion can move from this direction to another direction. And if the spike is in this way, the skyrmion can come back. So the device could be like this in this picture, and this is one part, and this is another part. We can detect with the number of skyrmion. So as discussed this morning, to detect one skyrmion is very challenging. I think this is very difficult because today we can make a very small MTJ, but in order to control one synapse to pass through the free layer of MTJ, I think it's too difficult for challenge. But we can measure how many skyrmion in this free layer. So this is much easier to perform. So this is the device structure. And let's present with a movie how it works. So positive stimulus can make the skyrmion move in this side, and the negative will put back the skyrmion. And this barrier can be used a different method. So just to control it's the perpendicular magnetic anisotropy, we can control the level of this barrier, the energy barrier.
I'm sorry.
Okay.
There are two skyrmions that remain at the end of the simulation. Would they actually go on the other side if you actually increase the bias, or they would stay creating a dipole, skyrmion dipole?
Sorry?
I'm saying that those, look at the picture, you have two skyrmions, right, staying on the side, on one side of the barrier.
Yes.
So if I increase the bias, would they both go on the other side?
Yeah, yes,
okay.
yes. So this is represent the number of skyrmion in the pre-synapse and the post-synapse. So as you mentioned that we can change the voltage, the current density to control how many skyrmion pass through this barrier. So this device, the barrier controls the energy level, and the current, as Beihang current, can control the energy to move how many skyrmion in this pre-synapse and the post-synapse. In this case, in the detection side, by using magnetometer resistance, we can find.
Do you have a decay rate at the post for the post-synapse? Is there anything that corresponds to the post-synapse decay time, where the skyrmions decay over some time constant?
Yes, I think there is some decay behavior. I just, yeah, it's a good question because I will continue. So it's not very well. Okay, so there, one of the conventional behavior of synapse is it should have the short-term memory behavior. This means it should be possible to forget, and there is a long-term memory. That means if we strain, give this device very high strain or very high frequency strain, there should be a long-term memory. So if I understand, the decay is like short-term memory. This is the basic behavior of skyrmion. So we try to reproduce this behavior. So by using the different the pulse duration and its the ratio, so we can control for the case short-term plasticity. If the pulse is 1 duration with 5 nano interval, so we cannot give a long-term memory, and it's just a short pause. It means that there is some skirmion pass trying to attack the barrier, but it cannot pass through. But if we use a longer pulse with the similar interval, it's possible to get the skirmion pass through the barrier, and we can get the long-term memory. Another method is to use the similar pulse duration, but pulse duration with a lower interval. So in conclusion, so it's possible to get this biological behavior of synapse by using this device. So the physical picture is like that. So when the skirmion, a number of large skirmion pass through the behavior, so it presents long-term plasticity. If it's arrive this barrier, but it cannot, the current is not continuous to push the skirmion to pass through the barrier, it will come back. It will present the short-term memory. So in this case, we can design successfully synapse like device with skirmion. So the second synapse that we can imagine is to use skirmion creation in perpendicular magnetic tunnel junction. So this, when I write the review, it seems I calculate the energy efficiency by using spin Hall current. So we need always a very high current density to move the skirmion. But when we use a spin transfer torque method to nucleate the skirmion in the MTJ, the energy efficiency could be better. So this is why we focus also some device to implement the skirmion in magnetic tunnel junction. But in the conventional MTJ, it's very difficult to make this one because, as I mentioned, we need a very strong interfacial DMI, and we should have some method to nucleate some skirmion inside the magnetic tunnel junction. But in the perpendicular magnetic tunnel junction, for this design, we try to control its stray field. But if we regard what's the distribution of stray field in magnetic tunnel junction, you can find that in the edge part of the free layer, the field is very high, but in the middle it's low. So this is very interesting, and it gives the possibility to nucleate the skirmion in the magnetic tunnel junction. So that's why we perform intensive study. So how to make skirmion in magnetic tunnel junction. So if in this device there is a stray field but no DMI, so whatever we send the current from spin transfer torque, there are no skirmion. And if there is DMI but no stray field, there are no skirmion. But if we combine the intrinsic stray field and we integrate a large DMI, it's possible to have a skirmion in the magnetic tunnel junction. So the behavior of the switching is like that. In the case of parallel state, we send a current, and in this case we have this state, intermediate state, and by using a larger current we can get anti-parallel state. So this skirmion integration allows 3 states of magnetic tunnel junction. So some people ask, because we can send the current direction and this direction. It could be get four level of state, but the Skyrmion size in the magnetic tunnel junction is only defined by the straight field and the DMI value. So that's why it's three state. And this multi-state magnetic tunnel junction can be used like resistive memory to get multi-level for synapse-like device. So we continue to study if we have a larger scale DMI and a larger scale current density. So what's the perspective that we can get in the magnetic tunnel junction? You can find that in some case, when the DMI is around 2.5 and with a relatively large current, it's possible to get 4 or 5 Skyrmion in magnetic tunnel junction. So this is very interesting. That it means that the magnetic tunnel junction could be used to get multi-level like resistive memory for synapse. Okay, so this is a very the work two or 3 years ago. After that, I'm trying to find a system experimentally validated that we can get TMR, magnetic resistance, large DMI, and the straight field. So the system was in this structure, so platinum, cobalt, MgO. So some people already reported this can get a strong DMI. So based on this research, we performed a study to vary the thickness of MgO to regard if it's possible to have a very thin MgO layer. And in this case, we can get a large DMI like we use in the simulation. So 2.5 is the value that we expect to get many Skyrmion in magnetic tunnel junction. So we are lucky to find this system is possible. And in these experiments, we got a DMI around 2.6. As I mentioned in the last slide, 2.5 is already a barrier that to validate experimentally this device. So this is undergoing work, and I think it's, all the fundamental is ready. So but we need to fabricate magnetic tunnel junction to realize this multi-level magnetic tunnel junction. And the third part is Skyrmion-based neuron. Okay, for the neuron, there is the basic behavior is leaky, integrated, and fire. So this is the behavior of biologic neuron, and if we get Skyrmionic neuron, we should be able to reproduce at least this type of behavior, such as spiking in like that. And there is there is a threshold to fire, and then there is a spiking out to reset to this original region. So based on this structure, with the new Skyrmion, we define that the leaky means the Skyrmion move back around, and integrate is move forward. The fire is there. We can achieve a threshold, and the reset is the origin region. So this slide have been discussed this morning by Axel. So the first idea was based on this structure. So by using a wedge system, so with the variable ferromagnetic layer, we can get a linearly. We expect to get a linearly perpendicular magnetic anisotropy. In this case, the device, the Skyrmion can be moved automatically in this nanowire, because this wedge induce the change of interfacial PMA, and this PMA will drive the Skyrmion to move in this structure. So we perform the experiments to validate this idea. So this is exactly the similar structure. So we can get, so it's not perfect perfect line of PMA variation, but it's very similar to the structure that we expected, like this line. So it's possible to do it, but this is not practical. This is not practical. So how it works dynamically? If there is a uniform PMA, so the Skyrmion will stop without current. But if there is a gradient PMA, when we send a current in the nanowire, so Skyrmion will move. And if there is no current, the Skyrmion will come back due to this gradient change. So this is the behavior for the, as I mentioned, that this is integrate and this is leaky, and there is a distance to pass through, means there a fire. So we performed some parameters to evaluate this the speed and the behavior, how is it pass or not in the nanotrack. So this is with its geometry defined structure. But as I mentioned, that you can find we do require that the wedge system is able to get a linear change of PMA. So this is experimentally very challenging. That's why this proposal we proposed 2 years ago, but after deep thinking and these experiments, we think it's better to move another type of Skyrmion. So another type of the Skyrmion is based on the geometry defined. It's not in the wedge system. It's based on the shape-based. So 2 years ago, there is a structure based on anti-ferromagnetic coupled multi-layers. In this layer, the interesting thing is that we can avoid the Skyrmion Hall effect. So in this case, the Skyrmion will move directly from this side to this side, and we will not touch the edge. And we can move as the similar strategy is will move in this side to this side to define its working condition of this neuron. Okay, so the device is look like that. There is a structure like that. So from this side, we can nucleate the Skyrmion in this part, and then we send the Skyrmion from this side to this side, and here we detect the Skyrmion with a magneton junction effect. So you can see that in the biological neuron, the control of this behavior is also something like this with its shape. So this is why we think that maybe this idea by using its shape defined Skyrmion behavior could be helpful for neuron design. So basically, the motion of skyrmion will be defined by two factors. So one is the spin Hall current. So when we send a current, the skyrmion will go this way, and when the current goes higher, it's possible that the skyrmion pass through this area. And when there is no current, there is a force from the edge. So the edge will get a force in this side, and this force in this side, and for the two directions, though, the force will be eliminated, but we can create a direction in this back direction. This is why when there are no current, just put a skyrmion here, it will move in this side. So this is a leakage operation of the neuron. So there is some factor to define how to make it correctly. So there is some relation between the L, this distance, and also this geometry. Okay, so in this case, we tried a different mode of wave, like square, sinusoid, and triangular. So you can find that there is a integrate behavior and there is a leakage behavior if the pulse will be stopped, and we started all the behavior. The structure for different L is the distance from here to here, and B is this west. So you can find there are for the this red circle is a stop, and for the this is a path. So by using this method, it's much easier to make working neuron by using Skyrmion. So in conclusion, that I show you three devices based on Skyrmion towards Skyrmionic neuromorphic computing. Actually, one of the my focus experiments is MTJ-based synapse, but I think this new neuron based on gradient width dependence is also possible for the nanofabrication, and this is our next step working on this direction. Okay, thank you very much for your attention.